Let me step back and look at self-driving cars from a completely different angle. You know how everyone talks about these vehicles like they are some kind of mystical future technology. Here is the thing that will blow your mind. Take your average teenager learning to drive. They can glance at an intersection for half a second and instantly know whether to brake, accelerate, or prepare for that awkward moment when they stall at a traffic light. Meanwhile, a self-driving car worth more than your house needs multiple sensors, piles of software, and the processing power of a small data center just to do the same thing. Why is something so natural for humans so incredibly complicated for machines? Today I'm going to walk you through exactly how autonomous vehicles work, and I promise by the end you will understand why this technology is simultaneously the most impressive and the most fragile thing we have ever put on wheels. If you like tech explained without the headache, subscribe because this channel is basically me turning confusing systems into simple stories you will actually remember. You will also know why your robot chauffeur might get spooked by a plastic bag, but can parallel park better than most driving instructors. Let us start by clearing up the biggest misconception about self-driving cars. Most people imagine them as these brilliant artificial minds that somehow understand the world like we do it. That is completely wrong. Think of an autonomous vehicle more like an incredibly paranoid librarian who has been given a massive reference manual and told to follow rules very carefully. This librarian has superhuman senses, but basically zero gut instinct. They can spot a pothole from far away, but they might hesitate if they see a situation that is rare, messy, or not clearly covered by what they have learned. The whole system works like a three-person team where each member has one very specific job. The first person is the observer, whose only task is to constantly describe what is happening around the car. The second person is the decision maker, who uses those observations to choose a safe plan. The third person is the driver, who physically carries out that plan by steering, braking, and accelerating. None of these team members can do the other's jobs, and they pass information back and forth dozens of times every second. Let me break down how the observer part works, because this is where things get really interesting. While you navigate the world using two eyes and some common sense, self-driving cars rely on a bundle of sensors because each one sees the world in a different way. One of the most famous sensors is Lidar, which stands for light detection and ranging. Picture it like a magical measuring flashlight. The car sends out tons of invisible light pulses and measures how long they take to bounce back. That gives the car a detailed, three-dimensional outline of its surroundings. It can figure out where objects are, how big they are, and whether they are moving toward or away from the vehicle. Imagine you are in a dark room trying to understand the layout by throwing ping pong balls everywhere and listening for where they bounce back from. Lidar works similarly, except it is throwing light instead of ping pong balls and doing it thousands of times faster than you ever could. This gives the car something like supernatural spatial awareness. But here is where Lidar hits its limitation. Even when it is great at shape and distance, it does not automatically understand meaning. It can tell you there is a flat rectangle on a pole, but that alone does not tell you whether it is a stop sign, a speed limit sign, or a billboard. That is where cameras become critical. Regular cameras positioned around the vehicle give it something closer to human vision. Cameras can see color, read sign shapes, notice lane markings, and tell whether a traffic light is red or green. Think of cameras as the part of the system that adds context to all those measured shapes. The collaboration between LiDAR and cameras is like having a friend who is amazing at measuring distances but struggles with details, paired with another friend who sees details clearly but is not perfect at depth. Together, they are stronger than either one alone. One system says there is a tall pole with a flat sign. The other system says that sign is red, octagonal, and means stop. Then there is radar, which solves a problem neither LiDAR nor cameras handle perfectly. When weather gets ugly with heavy rain, fog, or snow, camera vision can get messy, and LiDAR can get noisy too. Radar uses radio waves, which can punch through conditions that make light-based sensing struggle. Radar is especially good at telling you that something big is ahead and how fast it is moving relative to you. How fast it is. Radar works like an enormous game of Marco Polo. The car sends out signals, they bounce back, and the car learns there is an object out there and how it is moving. Radar does not paint a crisp picture like cameras, and it does not build the same kind of dense 3D map Lidar can, but it is a reliable way to keep track of motion in bad conditions. Now that we have covered how the car observes its environment, let us talk about the decision-making process, which is probably the most misunderstood part of autonomous vehicles. The car brain is not daydreaming or improvising like a human. It does not have intuition. It does not get a weird feeling about a driver who looks suspicious. Instead, it takes what it sees, predicts what might happen next, and chooses a plan that tries to stay safe and legal. Some parts of this are rule-based, like basic traffic laws and safety constraints. Other parts are learned from data, like recognizing objects, estimating where lanes are, or predicting whether a pedestrian is about to step into the road. The important point is this: the car is constantly turning the world into a structured problem, then solving it over and over at high speed. This is also why autonomous vehicles need an absurd amount of testing. Every time the system runs into a weird edge case, engineers study it, improve the models, adjust the planning logic, and make sure the car handles something similar better next time. It is like building a library of real-world situations, one hard lesson at a time. The third part of this three-person team is what engineers call the actuation system, which is basically the car hands and feet. Once the brain decides what to do, it needs a way to physically control the vehicle. That happens through electronic systems that steer, brake, and apply throttle with precise commands. When the brain decides the car needs to change lanes, it sends signals to the steering system to turn the wheel by exactly the right amount. If it decides stopping is necessary, it activates braking with controlled pressure. If it needs to speed up smoothly, it commands the accelerator. Unlike human drivers who sometimes overreact or hesitate, these systems do exactly what they are told, consistently, every time. The whole loop, from sensing to thinking to acting, happens continuously, many times per second. Observe the world, predict what is about to happen, choose a plan, execute the plan, repeat. When it works well, it looks effortless. But under the hood, it is a very rigid machine doing an insanely fast cycle of perception and planning. So what does this mean for you as someone who might encounter these vehicles on the road or consider buying one in the future? Understanding how self-driving cars actually work explains both their impressive strengths and their frustrating limitations. If you drive mainly on highways with clear lane markings and predictable traffic patterns, automated driving features can feel almost magical. They do not get tired, they do not text and drive, and their reaction timing can be extremely consistent. If you spend a lot of time in construction zones, rural roads with faded markings, or chaotic city intersections with unpredictable behavior, you should know these are still hard problems. The technology works best in environments that look like the environments it was trained and tested on. If you are thinking about safety, autonomous systems can be strong against accidents caused by classic human failures like distraction or fatigue. But they can also make bizarre mistakes when the world looks unfamiliar, when sensors get confused, or when the situation is ambiguous in a way humans handle with social intuition. And if you are thinking about convenience, remember that many systems today still require supervision and can ask you to take over in tricky moments. The fully hands-free robot taxi dream exists in limited, carefully controlled areas, not everywhere and not in every condition. Here is my simple framework for thinking about autonomous vehicles. They are incredibly sophisticated tools that can follow patterns and rules with amazing consistency, but they still struggle with the messy creativity humans do without thinking. As the tech improves, the safe and reliable operating zone will expand, but the edge cases are the real battlefield. The key insight is that self-driving cars are not trying to copy your brain. They are trying to reach the same goal of safe driving using totally different methods. Sometimes that makes them better than humans. Sometimes it creates brand new failure modes that humans would never even consider. So there you have it. Self-driving cars are basically paranoid, rule-following robots with superhuman sensors, fast reflexes, and a giant decision pipeline running on repeat. They can park like a pro and react instantly, but they might also hesitate over something as silly as a plastic bag blowing across the road. They are not magic. They are sophisticated machines doing their best to turn the chaos of the real world into something they can compute. If this helped demystify autonomous vehicles for you, hit subscribe for more clear, no-jargon tech explanations from Tim. The goal here is simple: help you understand the technology you use and see every day so you can feel confident, informed, and in control as it becomes more common in real life.